Boosting an ORBASED computational protein design. Dynamic heuristics and generalizable UFO. This research enhances the scalability of the AOBB-K algorithm for protein redesign. AOBB-K is an exact and/or branch and bound approach that showed competitive performance with BBK on small protein problems but lacked scalability. The authors introduced three new versions: AOBB-KB, boosted, AOBB-K DH, with dynamic heuristics, and AOBB-K UFO, with underflow optimization, to address this limitation. These modifications aim to improve the efficiency of the search process. The paper includes an empirical analysis of these schemes on 62 real protein benchmarks, comparing them with previous AOBB-K and state-of-the-art BBK. The computational protein design field involves modifying known proteins to alter their functions or interactions. Amino acid positions are deemed mutable, and a preferred sequence is determined through sets of mutations, estimating the resulting protein's quality based on potential conformations. Simplifications are made, such as limiting mutable residues, discretizing sidechain conformations, and assuming a fixed protein backbone. This leads to algorithms identifying mutations enhancing protein functionality. The affinity between protein subunits is related to the binding and dissociation rates, described by the equilibrium constant K. To compare K values, protein subunits are synthesized through molecular processes. A graphical model can be defined for KMAP, aiming to maximize protein-ligand interaction by finding an amino acid assignment that maximizes K. This model resembles the determination of marginal maximum a posteriori, MAP, leveraging similar graphical model algorithms for optimization. The CPD is formulated as a graphical model, where variables represent protein residue positions and conformation variables, aiming to maximize protein-ligand interaction. The authors present a probabilistic graphical model for protein redesign, where each residue is represented by a random variable Re, accompanied by conformation variables C gamma, I, representing the spatial conformation of the assigned amino acid. Each Re has a domain consisting of possible amino acids, and the amino acid assignment to Re acts as a selector into the possible assignments to C gamma, I. The model includes constraints C to ensure that the assigned rotamer to C gamma, I, belongs to the amino acid assigned to Re. Energy functions ESB gamma and EPW gamma capture the energies of interaction of the amino acid at each residue I with itself and the surrounding backbone, and pairwise energies of interaction, respectively. The objective function is defined as K** operator, R, equals ZB, R, ZU, R, where Z gamma, R, is the partition function of the protein subunit in state gamma. The task is to find the maximum a posteriori, MAP, value of K** operator, denoted as K** operator MAP. To optimize K** operator, the authors employ an exact branch and bound algorithm called AOBB-K operator, which constrains solutions such that the partition function of each protein subunit is greater than a biologically relevant subunit stability threshold. The algorithm takes a conditional probability distribution, CPD, graphical model as input and outputs the K** operator map value of an optimal amino acid assignment to the residues. AOBB-K operator is empowered by constraint propagation and traverses an underlying and/or search tree, pruning nodes whenever any of three conditions are triggered. The algorithm uses a mini-bucket-based heuristic called WMBE-K operator, which is adapted for K** operator map and operates similarly to its corresponding scheme for maximum a posteriori, map, inference. WMBE-K operator takes a variable ordering that constrains maximizations to be processed last and partitions functions into buckets, making a bounded approximation for buckets with a large width. The time complexity of AOBB-K operator S search is exponential in the depth of the search tree, while the space complexity is linear in its depth. The time and space complexity of WMBE-K operator are exponential in the I-bound I. Algorithm 1. AOBB-K has been advanced to improve its scalability, resulting in the boosted version, AOBB-KB. The original AOBB-K algorithm was limited by the sometimes weak or unbounded heuristic estimate provided by WMBE-K. To address this, AOBB-K introduces three sequential improvements to WMBEK. First, adjustments are made to the power sum mechanism to enforce non-zero lower estimates. This is achieved through the use of zero-emitted weighted functions and power sums. Second, the cost shifting mechanism is modified to prevent cost shifts with zeros. Finally, maximization with finite values over infinite ones ensures consistent subproblem bounds. These enhancements aim to produce more accurate and reliable estimates. The refined WMBEK heuristic estimate in AOBB-K provides non-zero lower bounds, prevents cost shifts with zeros, and maintains consistent subproblem bounds. This enables AOBB-K to tackle complex problems more effectively, making it a significant improvement over the original AOBB-K algorithm. In this section, the authors propose a novel approach to enhance the performance of the AOBB-K algorithm in solving protein design problems. They introduce three key enhancements. 1. Utilizing weighted mini-buckets to retain and enhance bounds. 2. Tuning the search by prioritizing the wild-type assignment and nodes with finite heuristic values. And 3. Employing dynamic heuristic recomputations during search to further enhance bounds and pruning. These adjustments are encapsulated in the AOBB-K DH algorithm, which leverages a general framework for dynamic heuristic use with AOBB-K. The first enhancement, weighted mini-buckets, modifies the cost-shifting mechanism to ensure that only non-zero values are considered, thereby preventing numerical instabilities and guaranteeing a positive lower bound for consistent subproblems. This adjustment does not disrupt bound guarantees. The second enhancement, tuning the search, prioritizes the exploration of nodes corresponding to the wild-type protein assignment, as it is known to be a good initial variable assignment in protein redesign. Additionally, nodes with finite heuristic values are given preference in the node ordering, ensuring that consistent configurations are explored first. The third enhancement, dynamic heuristic recomputations, is implemented in the AOBB-K DH algorithm. This approach allows for recomputing K upper bounding heuristic conditioned on the current search path at each node expansion, but only if certain conditions are met, such as not exceeding a specified maximum depth or heuristic estimate threshold. This helps regulate the frequency of these costly computations and ensures that K heuristic tables are rolled back to previous computations when backtracking. The AOBB-K DH algorithm is proven to be correct and complete, as stated in Theorem 4.1. It uses an upper bounding heuristic function and operates under the assumption that the input graphical model is in CNF form. The algorithm iteratively expands nodes guided by the pseudotree, updates heuristic estimates, and prunes or backtracks as necessary based on the current search path and heuristic values. Optimizing the K value for a given amino acid configuration is crucial for ensuring subunit stability. To achieve this, dynamic heuristic recomputation is employed, which bounds the time complexity at O, K max depth plus I, where K represents the maximum domain size. This approach is cost-effective when the number of nodes explored with dynamic heuristics, denoted by lambda dh, exceeds the number of nodes explored without dynamic heuristics, denoted by lambda. To further enhance the efficiency of solving K optimization problems, the algorithm incorporates constraint propagation, which prunes inconsistent search paths. This integrated approach enables the identification of optimal solutions more rapidly. The UFO scheme is introduced as a means of selecting an underflow threshold through binary search, ensuring a consistent model. This process initiates with an initial threshold and iteratively converges on the largest threshold that yields a satisfiable model. By optimizing the K value and leveraging dynamic heuristic recomputation, constraint propagation, and the UFO scheme, the proposed approach effectively resolves complex K optimization problems. Algorithm 5, AOBB-K UFO, presents a novel integration of the UFO scheme with the AOBB-K algorithm, specifically designed to tackle constrained protein design problems. The input parameters include a molecular CPD, a wild-type assignment to X, a SAT solving algorithm, a time limit, a deflation factor, a pseudo-tree guiding the search, and two upper bounding heuristic functions. The algorithm returns an approximation to the true KMAP. A key modification to the UFO scheme involves performing underflows on the Boltzmann transformed S and EPW functions, ensuring a lower bound on the quality of solutions. This adapted scheme has potential applications in various graphical model tasks beyond CPD. The empirical evaluation of the proposed algorithms is conducted on benchmarks derived from redesigned problems for real proteins. The experimental methodology involves incrementally increasing the problem size by making more residues mutable. 5 algorithms are compared: AOBB-K, AOBB-KB, AOBB-K AOBB-K UFO, and BB-K, a state-of-the-art best-first search algorithm. The results show that AOBB-K outperforms AOBB-K in terms of solution quality and speed on the expanded benchmark set. The dynamic heuristic scheme is evaluated, demonstrating its ability to reduce the size of the explored search space. AOBB-K UFO is also shown to be effective in finding high-quality solutions. Notably, the limitations of the algorithms are acknowledged, including the loss of optimality guarantees when using the UFO scheme and the non-completeness of the AOBB-K algorithms. Future work may involve exploring the UFO scheme for other graphical model tasks. The performance of AOBB-K is compared to AOBB-K on benchmarks with 3 mutable residues from Pezeshki et al. 2022, in Table 1. Dynamic heuristic recomputation reduces the size of the traversed search space in most problems, although it may increase the search space in some cases. This is because dynamic heuristic recomputation can cause the K estimate for a node to increase, preventing the node from being pruned. Table 2 compares the explored search space of AOBB-K with and without the use of a dynamic heuristic, demonstrating the effectiveness of dynamic heuristic recomputation in reducing the size of the traversed search space. The performance of AOBB-K UFO, AOBB-K DH, AOBB-K and BB-K is compared in Table 3 on problems with 3, 4, and 5 mutable residues. AOBB-K UFO is competitive with BB-K, and AOBB-K DH is able to find good solutions, sometimes better than BB-K. However, AOBB-K schemes struggle on problems with 5 mutable residues due to the loss of bounds from the boosted modifications of WMBE-KB, heavy underflows, and longer message passing. The ranking of the algorithms is based on the quality of K found and the speed at which the solution was first discovered. The results demonstrate the competitiveness of the UFO scheme and the potential of AOBB-K DH in terms of runtime. The determinism of Wembekbe's computed messages for AOBB-K UFO is evaluated, showing that for problems with 5 mutable residues, the largest tables generated by WMBE-KB often have a determinism ratio of greater than 0.95. This insight adds motivation to explore more compact representations that could enable the use of higher I-bounds. The comparative analysis of protein redesign algorithms, specifically AOBB-KB, AOBB-K DH, and AOBB-K UFO, reveals distinct performance profiles in terms of scalability and efficacy. Notably, the UFO algorithm demonstrates strong performance when applied to problems involving 5 mutable residues, suggesting its potential for tackling complex protein design tasks. AOBB-K DH shows promise due to its ability to explore a vast search space, which could be beneficial in solving larger problems. However, the current implementation of this algorithm is limited in its capacity to handle such tasks effectively. The study also highlights the potential benefits of employing more compact representations within these algorithms, as well as future directions for improvement. These include modifications to the WMBE-KB heuristic, adapting richer dynamic heuristics, and exploring the utility of UFO in other graphical model tasks. The findings underscore the importance of continued research into the development and refinement of protein redesign algorithms, with a focus on enhancing their scalability, efficiency, and adaptability to diverse problem sets. Please provide the original transcript that needs to be refined, and I'll transform it into a concise, technically accurate summary suitable for voiceover narration. I'll ensure that the refined text maintains the technical accuracy and depth of the content, explains key terms and concepts with precision and clarity, and highlights novel ideas and significant findings. Computational protein design relies on optimizing stability and binding affinity in protein-protein interactions, which can be achieved through the use of and/or branch and bound search algorithms. Guaranteeing diversity and optimality in these designs is crucial, as is the need for efficient search techniques that can navigate large sequence spaces. Anytime Anyspace and/or best first search algorithms, introduced by Qi Liu, Rina Dechter, and Alexander Ihler, are essential for bounding marginal map and solving complex optimization problems in computational biology. These algorithms are particularly important when dealing with large combinatorial spaces. Cost function networks, as researched by Manon Ruffini, Yelena Vucinic, and others, play a vital role in protein design by predicting changes in binding affinity. These networks enable the design of protein-protein interactions with guaranteed diversity and optimality. Positive multi-state protein design, explored by Yelena Vucinic, David Simoncini, and colleagues, aims to design proteins that can adopt multiple stable conformations, thereby enhancing their functionality and adaptability. This approach has significant implications for protein design and engineering. The efficient exploration of large sequence spaces and the guarantee of diversity and optimality are critical challenges in computational protein design. By leveraging and/or branch and bound search algorithms, cost function networks, and positive multi-state protein design, researchers can overcome these challenges and develop novel protein-protein interactions with improved stability and binding affinity.